students, welcome to Biology Made Easy. Today we'll be talking about the next part in the transcription in the prokaryotic system, which is known as the elongation part. In my previous two videos I have explained in depth about the initiation part 1 and part 2, where I have explained to you, I have done the in-depth analysis of the antisense, sense, the molecular dynamics of the open, closed and the ternary complex, how the coenzyme and the holoenzyme formation takes place, abortive initiation and so on. In this video, I will be exclusively talking about the elongation step, and I will be acquainting you to a very new topic known as the autoinhibitory domain of the sigma factor. So have you ever wondered why does sigma factor is unable, or why is the sigma factor unable to bind to the promoter sequence when it's all alone? Or can it bind? No, it can't. If it could, then the need of it to bind with the core RNA polymerase enzyme would be nullified. So what happens is, when the sigma factor is all alone, then the thing is, it has an N-terminal autoinhibitory domain. This domain masks its binding site with the promoter region, and when it does bind with the core RNA polymerase complex, the alpha, beta, beta dash and omega, then that binding induces a conformational change, which then takes this N-terminal autoinhibitory domain, shifts its location away from the site. It's not able to mask the site of the promoter binding region in the sigma factor. So that site gets unmasked, and then this sigma factor can recognize and bind to the promoter region efficiently. Now at this point of time, it has crossed the abortive initiation process and it's become pretty stable, the nascent mRNA transcript which is being synthesized. Now what happens is, this is the 3' OH group. It attacks nucleophilically on the upcoming substrate, which is the ribonucleotides, NTPs, and this is the template, which is deoxyribonucleotides, DNTPs you can call. Now this reaction fundamentally occurs due to the catalytic activity beta dash of the core enzyme of the RNA polymerase. By this point of time, the thing is, the sigma factor must have got dissociated in most of the cases, not all, but in most of the cases. So I'll be taking it as the core RNA polymerase enzyme, not the holoenzyme. Now when it keeps on synthesizing this mRNA molecule, the thing that RNA polymerase core enzyme encounters is a pretty grave problem. The problem is, it has to hold on to the template strand, it has to hold on to the substrate at its active site and then catalyze the reaction, and it has to hold on to the product also, which is the mRNA molecule itself. So it's a three-way process. So if it has to do so much, if it has to address so many problems, the possibility of it swaying around becomes more. So what it does is, how it maintains its stability and efficiency lies in the dynamics of the 3D structure of the RNA polymerase molecule. If you look at it closely, if you dig deep at it closely, then you will find that there is a thing known as trigger loop, which is a domain in the RNA polymerase molecule, and the proposed mechanism is the Brownian ratchet mechanism. The trigger loop, what happens, it stays in the unfolded state when the NTP or the substrate is not bound at the active center of the RNA polymerase core enzyme. And when the NTP does bind to the active site or to the active center of the RNA polymerase core enzyme, the trigger loop switches its conformation drastically and becomes folded again. In that folded state, the RNA polymerase becomes pretty stable. It holds on to all the three things at one go. And then when the RNA polymerase translocates from this nucleotide to this nucleotide in the DNA template, then the trigger loop again undergoes a drastic configurational change and switches its conformation from the folded state, previously folded state, to the unfolded state. And this cycle keeps on recurring, and thus this process gets underway without any kind of mishappenings. Now, the next thing is stalled RNA polymerases. Stalled means it hits an abrupt end. It becomes ceased. How does it stop? The thing is, if the RNA polymerase core enzyme encounters a nick within the gene, within the DNA of the gene, and it couldn't have been or that nick was not rectified by or via non-homologous end joining pathway or the homologous end or the simple homologous recombination pathway, then the RNA polymerase has no choice. It's left with no choice but to make a bypass jump but to bypass it or and that bypassing is done by jumping across. So when it does so, what happens it loses its what to say binding towards the 3-OH group. During the bypass jump, the RNA polymerase could get translocated from this point to this point. And we knew for sure that the RNA polymerase has to have its active site at the 3' OH group in order to catalyze the reaction of NTPs, because NTPs had to be added at the terminal 3-OH group, it cannot be added anywhere in between to form the new phosphodiester bond. Now what could be the plausible solution to this problem? How to resolve this case? The most promising aspect or the most promising hypothesis could be to trim these few ribonucleotides or the mRNAs from the RNA or from the mRNA itself, so that the RNA polymerase, which is now bound here, encounters the 3-OH at its terminal end. So in order to achieve this rigorous task, we have some nucleases in the Escherichia coli prokaryotic system known as the GRI-A and GRI-B, which bind at the terminal 3-OH group where the RNA polymerase is unbound, because if RNA polymerase was bound there, it couldn't have bound in the presence of RNA polymerase. Then it starts trimming, it initiates its trimming mechanism, and when it encounters the RNA polymerase, when it reaches its very vicinity, it then switches off its activity. It then releases itself. And now the RNA polymerase again gets translocated or not translocated, it again gets itself placed at the 3-OH terminal end, and the synthesis of the mRNA molecule initiates again, right? So that's about it in the elongation part. If you have any queries, any doubts, any hardships, then do post your queries in the comment section below. If you have liked this video, then please do not forget to hit the subscribe button, the like button, and do ring the bell if you want to know more about my new videos whenever I upload them. Thanks a lot.